Alright, so let's start with this one. Limit of functions. Limit of functions. Limit of functions at a point. So this time around, not infinity. You are moving at a point. At a point. So the function as x is approaching that point at that function. Alright, so let's see. So with this, write it as the limit as x approaches a. So we assume a to be what? The point of this f of x. So what will be the limiting value of that? What will be the limiting value of that? What will be the limiting value of that? So now, with this question, we are dealing with type 1. We have several types. So we are starting with type 1 of this question, of this topic, so that you know what is going on. You have to understand limits properly. They are very, very simple, but heed to the advice of what we say or we do here, right? So you check the way the steps are going, the way things are done, then you know how to tackle them when it comes to you, right? You know how to deal with them. So you have to check the limits very, very properly. So now let's deal with what? Rules. The rules of functions at a point when it comes to limits. The rules of functions at a point when it comes to limits. The rules of functions at a point when it comes to limits. When it comes to limits. So number one rule. It says that if we have the limit as x approaches a, that's the point a, of this value k is equal to what? K. Where k is a what? Is a constant. Where k is a constant. Where k is a constant. Then 2. The limit as x approaches this a of this x to the power n should be equal to, now with this, as x is approaching a, we just what? Plug in, wherever you see x, we just plug in a. So it becomes as what? A to the power what? N, right? Where a is a member, where a is a member of the real number, and n is a positive, and n is a positive integer, and n is a positive integer. So that's the symbol for integer. Then 3. The limit as x approaches a of, we have this, which is the nth root of x. This x, the nth root of x, the nth root of x. So wherever you see a, you just plug in what? X. You know that this nth root of x is the same thing as x to the power what? 1 on what? N. This one. I believe you did indices, so you know what I'm talking of here. So which is the same thing as, it will be what? The nth root of a, right? The nth root of a, where 0 is less than a. Where 0 is less than a should be a member of the real number. Should be a member. Sorry. Let's see. Where a is a member of the real number and n is an odd positive integer. Let me give you it properly. So the limit as x approaches a of the nth root of x equals, you get what? The nth root of a, because wherever you see x, you plug in what? A. So we get this. Where a is a member of R, where a is a member of R, and n is an odd positive integer. It's an odd positive integer. And n is an odd positive integer as that. And n is an odd positive integer. So, and n is an odd positive integer. So we have this. We have this. Alright. So we can say where, also we can give this one again as, the limit as x approaches a of this nth root of x, which the answer will be what? The nth root of what? A. The nth root of a. The nth root of a. So we have this, the nth root of a. Now, where 0 is less than a, should be a member of R, the real number, and n is an even positive, and n is an even positive integer, and n is an even positive integer. So what this one means that we can get this nth root of this x to be what? The n can be 3, that's an odd number. Then the n can be 2, that's an even number, right? So we can get it as that. So that's that. So right, so let's move on to the fourth rule. I believe you understand this one. So we have the first one, which is the limit of k as x approaches a, which is equal to k, where k is a what? It's a constant, right? Then the limit of x to the power n, where x approaches a equals what? A to the power n, where a is a member of what? The real number, and n is a positive what? Integer. Then also the third rule, the limit as x approaches a of what? The nth root of x equals the nth root of what? A, where a is a member of the real number, and n is what? It's an odd number or odd positive integer. Then with this the same thing, we can get n to be what? An even integer, an even positive what? Integer, an even positive integer. We don't want even negative, we want even positive, right? Even positive integer. All right. Let's go to the fourth rule. Let's go to the fourth rule. The fourth rule. The limit as x approaches a of b to the power x equals, so wherever I see x, I place in what? A. So I'll get b to the power what? A, where a is a member of the real number and b is a positive real number, and b is a positive real number, and b is a positive real number, and b is a positive real number. Then 5, what we did, we know that the limit as x approaches a of f of x plus or minus g of x of that. So as x approaches a of this function, plus or minus, is the same thing as what? The limit as x approaches a of f of x. You can do for the plus, so plus the limit as x approaches a of this g of what? X, right? Then you come and do for the subtractional sign, right? So which is what? The limit as x approaches a of f of x minus the limit as x approaches a of what? G of x. So it's the same thing. What we did for what? The infinity as x approaches infinity. It's the same thing when we are doing for as x approaches infinity. If and only if is that. Alright, so let's move on to the sixth rule. The sixth rule. The sixth rule. So you have to take note of the rules of limits so that it can help you in your workings. So the sixth rule. We have the limit as x approaches a of this k times g of x. So g of x is a what? It's a function in terms of what? X. So now this one, it will be the same thing as what? The limit as x approaches a of what? K, then times the limit as what? X approaches a of this g of x. Of this g of x. Of this g of x. So we have it as that again, the limit of k as x approaches a. This one is the same thing as k times the limit as x approaches a of g of x. Then we have 7. We have the seventh rule. We have the seventh rule, which is the limit as x approaches a of f of x all on g of x, provided this g of x is not equal to 0. So we can take it as what? We can take this as the limit as x approaches a of f of x all over the limit as x approaches a of g of x. Of g of x. Provided this limit as x approaches a of this g of x is not equal to what? 0. It's not equal to 0. So watch it very carefully. Alright, so let's proceed. Let's proceed. So we are done with the rules of limit. We are done with the rules of limit. We are done with the rules of limit. Oh, sorry. I didn't give you this. The limit as x approaches a of f of x times g of x. That's a product. When you get the product of this function, it's the same rules in the as x approaches infinity. It's the same thing you apply here, right? So which is the limit as x approaches a of f of x times the limit as x approaches a of this g of x. Very simple. Very simple. All right. So that's that. That's the 8th rule. So we are done with the rules, right? So we take notes of them properly. We take notes of them properly. So let's note something here. Let p of x be a polynomial and let a be a real number. Then the limit as x approaches a of that p of x must be equal to p of a. The limit as x approaches a of this p of x. I told you that when you see, wherever you see x, we are placing or we are substituting this value a. So we get to p of a. So that's what we are saying here. Hence, the limit of polynomial function at any real number can be found by what? Substitution. So it can be found by what? Substitution. I already said we are doing the type 1 of this. So type 1 of this limit of functions at what? At a point. At a point. I know what I'm saying, because it's not always when you get the limit as x approaches a point of that function, then you substitute. No. There can be a case you have to simplify the function. But with this type 1, I'll just give you functions that you can do what? Direct what? Substitution. I believe you understand what I'm saying. I said not always you get a function, you can do what? Direct substitution into the function. When you do, sometimes when I give you a function, then you just do the direct substitution into the function may or will not what? Exist anymore. So not always you do the direct what? Substitution, but sometimes you have to do what? Simplification. You have to simplify, or you have to reduce the function to its what? Lowest term. So that's why we are dealing with what? The type 1 of this limit of functions at what? At a given point, or at a point, right? Okay. So that's the limit as x approaches a of this p of x equals what? P of a. So this one is found by what? Substituting. So I can say the direct substitution of that. All right. Then again, note that let p of x and k of x be polynomials and let a be a real number. Suppose that k of a is not equal to 0. So again, we have this, the limit as x approaches a of this p of x, all on this, let's say k of x, provided this k of x should not be equal to 0. If this k of x is 0, then that means the function does not exist, right? Okay, so provided this k of x is not equal to 0, then we have this. We have the limit as x approaches a of this p of x, all on k of x. So wherever you see x, you substitute what? A. So this one is done by what? Direct what? Substitution. So I'll get what? P of a all on what? K of a. So that's how we do the limits for direct substitution, right? So P of a all on K of a for that. Okay, so we are starting with what? Example. So with this type 1, we are only doing what? Direct substitution. But for the type 2, you know where I said we don't do direct substitution. So that's why I said when they give you the limit function, or when they give you the function and they tell you to find for the limit, you have to check the function very, very well. Before, check whether the limit as x, is it approaching a certain point, or the x is approaching infinity before you start. Do you understand that? So you have to relax, but solve more questions on that so that you'll be conversant with some of the questions, or you'll be comfortable with some of the questions, then you can do it properly. All right, so let's start with examples on that quickly. Let's start with examples on that. So 1, you have examples, we are dealing with examples here. We are dealing with examples here. 1. Find the limit as x approaches a. As x approaches 4. So now our a is what? 4. Of this 1 plus x to the power 2, if it exists. If it exists. So we have to find for the limit as x approaches 4 of this function 1 plus x squared, if it exists. So we are going to look for the limiting value as this function approaches what? 4. This function, as x approaches 4 for this function here. Very, very simple. Very, very simple. You have to listen. So this one, we are doing what? Direct what? Substitution with this function. We can't do simplification here because we cannot simplify this function. Or 1 plus x squared is x squared. No. 1 plus x squared is still 1 plus x squared because what? They are unlike what? Terms. So we do direct substitution. So solution, I still write the question again, the function, which is 1 plus x squared. So the limit as x approaches 4 of this 1 plus x squared is found by what? Substituting wherever you see x, replacing what? 4. So I get 1 plus 4 all squared, which must be equal to 1 plus 4 all squared is what? 16, which must be equal to what? 17. So the limit as x approaches 4 of this 1 plus x squared is what? 17. So this is the limiting value. That's the limiting value. That's the limiting value. So we can see the behavior of this function as x is approaching 4. What will be the behavior of that function? So the behavior of this function will be what? 17. Very, very simple. So this one is what? Direct substitution. Very, very simple. Very, very simple. Or you can, or this one you can, okay, let's go, or let's do it step by step. You can choose to do it step by step. As you can take it as the limit as x approaches 4 of 1, then plus the limit as x approaches 4 of x squared. Right. So you can try and do it like this. You go step by step. So we know that the limit of 1 as x approaches 4 is the same thing as what? 1. Then plus the limit as x squared. The limit of x squared as x approaches 4. So the limit of x squared as x approaches 4. We can do direct substitution here, which is 4 squared, which will give me 1 plus 16, which is what? 17. Very, very simple. Very, very simple. Very, very simple. So this one is type 1. We are doing direct what? Substitution. Direct substitution here. We are doing direct substitution. Alright. So let's see the second example. The second example here. The second example. It reads as what? Find the limit. You should find the limit as x approaches 2 of x minus 1 all on x squared plus x squared plus x minus 2. If it exists, if this function exists, you should find for that. So now, let's get back. If this one is infinity, we would have what? Divided each numerator, each term of the numerator and each term of the denominator by what? The highest power of the variable, by the highest power of the variable. But this one is what? It's approaching a point, and the point here is what? 2, right? The point here is what? 2. So we can't do it like that. So now here we take it as what? The limit as x approaches 2 of x minus what? 1. I take the numerator, then also I take the denominator of the limits. So the limit here as x approaches 2 of x squared plus x minus 2 as that. Then also, if I have that, I can say that the limit as x approaches 2 of this x minus the limit as x approaches 2 of this one, all on the limit as x approaches 2 of this x squared plus the limit as x approaches 2 of this x, then minus the limit as x approaches 2 of this 2 here. So that's type 1 of this 2. Very, very simple. So the limit as x approaches 2 of this x, we just plug in that. So I have 2 minus this one. The limit as x approaches 2 of 1 is the same thing as what? 1. Because the limit of a constant gives what? The same value, or give the same constant. Then here I plug in, wherever I see x, I plug in 2. So I get 2 squared minus the limit as x approaches 2 of that x. I plug in the value x, which is 2, minus the limit as x approaches 2 of a constant value, which is the same thing as what? The constant. Very, very simple. So 2 minus 1 gives 1, all on 2 squared gives what? 4 minus 2 minus what? 2. Now, 1 on 4 minus 2 is 2. Then minus 2, which is what? 1 on 0. This one, 1 on 0. Oh, let me check the question well. 1 on 0. It can be possible for that. Let me check the question. Oh, sorry. It's supposed to be plus. So here is supposed to be plus. Because A. Okay, but I say no. It's supposed to be plus. So I'll get what? This one cancels that, right? This one cancels that. So we get what? 4. So That's good. So it's 1 on 4. So I made a mistake. It's supposed to be plus, I made it minus. So I made a mistake. Sorry. So that's that. What you are here. So that's that. So alright, so let's see the third question. So we can see that the direct substitution is very, very simple. Very simple. And also, if they give you the limit, I told you to this one is type 1, right? And I said there are some times you cannot do direct substitution. You have to do simplification. And also, if you cannot simplify the function, then that means direct substitution is what required of you, right? There are sometimes you can't do simplification. When you do it, it bounces back to you yourself. So you have to do substitution, and that will help to find for the limiting value of the function. Okay, let's solve the third example, which is the limit. Evaluate the limit as x approaches 3 of this x plus 5 all on x minus 1. So we have that. X plus 5 all on x minus 1. So this one, how would you do that? So let's proceed as that. So we take the limit of the numerator, which is x plus 5, all on the limit as x approaches 3 of x minus 1. Right? So this one, I can say that is the same thing as the limit as x approaches 3 of x plus the limit as x approaches 3 of 5 all over the limit as x approaches 3 of x minus the limit as x approaches 3 of 1. Right? So we have this. So now, the limit as x approaches 3 of this x, I said we plug in, right? So we have 3. Then plus the limit of a constant as x approaches 3 is the same thing as what? The constant. So plus 5. All on. The limit as x approaches 3 of this x, we plug in. So we have 3. Then minus the limit of a constant as x approaches 3 is the same thing as the constant. So minus 1. So I have 3 plus 5, which gives 8. All on 3 minus 1, we obtain what? 2. So 2 divides 8. Or 8 divided by 2, we get what? 4. So the limiting value here is what? 4. The limiting value here is 4. Right. Alright. Let me try the last example with you. The last example, that's the 4th example. This one is very, very simple. Or let me give it to you to try, right? Let me give it to you to try. It's very, very simple. So you try the last example. The last example. You try the last example. It is the 4th example. So they said evaluate the limit as x approaches 1 of this 3x minus 4 all on x plus 1. All on x plus 1. So you try this. I'm not trying that. You try that yourself. Right. Okay. So you try that yourself. So now we are done with what? Limit of functions at a point. We are done with limits of functions at a point for this type 1. So this one is type 1, which involves what? Direct substitution or substitution. Right? So we are done with limits of functions at a point for this type 1. But we are not done with that as a whole. Right? We have to move on to the next sub-topic under this limit of functions at a point. So now, watch very carefully. Watch very carefully. So this one is for direct substitution. Okay. So let's see. We are moving on to limits of functions at a point. At a point. But this one, we are focusing on the type 2 aspect. The type 2 aspect, which is what? Indeterminate forms of limits. Indeterminate forms of limits. Indeterminate forms of limits. This one, we are moving to indeterminate forms of limits. When you talk of indeterminate, we have 0 on 0. This one is indeterminate, meaning you cannot determine it, right? You cannot determine the answer for this. 0 divided by 0. What's that? Indeterminate. We have infinity divided by infinity. What's the answer? The answer is no. You cancel this, then you get 1. I beg you. Infinity divided by infinity. As it stands now, we don't know. But when you come and do higher mathematics, you know. So 0, so at your level, we don't know. 0 divided by 0, we don't know. So that's indeterminate. This one, somebody can say the answer should be 1, it should be 2, it should be 3, it should be 4, it should be any answer. So it's indeterminate. We don't know as it stands now. So now, how should we tackle this type of questions? Listen, so this one is type 2, under the limits of functions at a point, indeterminate forms of limits. So now, let me read something here to your hearing. If a rational function is undefined at x equals a, if a rational function is undefined at x equals a, if a rational function is undefined at x equals a, comma, it means that a does not belong to the domain of f. If a rational function is undefined at x equals a, it means that a does not belong to the domain of f. I believe you know domain. When you talk of domain, domain, you did rational functions, so you know domain. You did functions, relation functions and mapping. You did that, so you know what domain. So the domain of a function, there are values that when you plug into the function will be defined for that function. So the domain are what? The x values. When you plug in or when you substitute the x values into the function, it will be defined for that values. Again, domain of a function, they are what? The x values. But range is the y values. Range are y values. But domain are what? The x values. So when you plug in what? The x values into what? The function, it will what? Define. Not define. I mean not define. But here it will be defined for domain. So when you plug in any x value into the function, it will make the function what? Be defined for that. Do you understand that? Aha. So that's what the domain of a function. The domain of a function. So there are x values. When you plug into the function, it will be defined for that x value. So now here, the question says, or the note says what? If a rational function is undefined at x equals a, it means that a does not belong to what? The domain of f, right? Thus, when you substitute x equals a in the numerator and denominator, when you substitute x equals a in the numerator and the denominator, the result is what? 0 on 0. The result is 0 on 0. So which is what? Indeterminate. So the result is 0 on 0. The limit is said to be in the indeterminate form. The limit is said to be in what? The indeterminate form, which is what? 0 on 0. For example, let's see, for example here, what's something here? We want to see the indeterminate form. So, if you have the limit as x approaches 1 of x minus 1 all on x squared plus x minus 2. So this one, you have to do for the type 1. We did what? Direct what? Substitution. So for this one, let's plug in the x value, which is 1, inside. So we have what? 1 minus 1 all on 1 squared plus 1 minus 2. So we have 0. All on here will be 2 minus 2, which is 0 on 0. So this one, it is what? Indeterminate. Indeterminate. So this one, you cannot find the limit by doing what? Direct substitution. But rather, you can find for the limits by doing further simplification. So when you do the simplification, then before you plug in what? The x value. Do you understand that? So then you plug in the x value for that. That's x approaches what? 1. So this one, you have to simplify the function before you plug in the x value. So now, when x equals 1 in both the numerator and denominator, 0 over 0 is what? Is obtained as that. In this case, it is advisable to either factorize the numerator or denominator first, then simplify and take the limit at the given point. So, what we mean here, let me summarize what I just said. What we mean here is when they give you the limit question, or when they give you a question and they tell you to find for the limit as x approach a certain value or a certain point, my friend, you take your time. Don't just plug in the point inside the function, but just do further checks. Whether this I can simplify or I cannot simplify. If you can simplify it before you plug in the x value. But if you know that you cannot simplify the function, then you can go straight and plug in the x value. Alright, so let's start with an example here. Let's start with an example then. Let's see. So, question 1. I'm coming, right? Alright, so question 1, it says what? Find the limit. You should find the limit as x approaches 1 of what? X minus 1 all on x squared plus x minus 2 if it exists. If this function exists. So now here, you have to what? When you plug in 1 inside, when you do direct substitution, this function will not exist. It will be what? Indeterminate. We don't know. Right? We will not know the limiting value for that. Here, we are interested in the limiting value here. Right? So when you plug in 1, it won't move like that. So now here, we have to do what? We have to either factorize here. You have to factorize the denominator here. Factorization is the reverse of what? Expansion, right? So you have to factorize the denominator there. You have to factorize. So you can punch your calculator, then move on to quadratics, because the highest power here of the variable at the denominator is 2. So you can punch, then you move on. So we get x equals 1. We get x equals 1. X being equal to 1, then x being equal to minus 2, which means that we have x minus 1, then we have x plus 2 for that, right? So with this, I can say that the limit as x approaches 1 of x minus 1 all on, now this one, in place of this x squared plus x minus 2, these are the roots of this quadratic equation, or the solutions, or the factors. They are the factors of that. They are the factors, right? These are the solution or the root. So this one is a factor of that. This one too is a factor of that. So we can place this or substitute this in place of that. So I'll get x minus 1, then we have what? X plus 2 for that. Right. So with this, I can say that this one what cancels that. Right. So we have this. This one cancels that. So I'll get what? The limit as x approaches 1. So here it becomes what? 1 all on what? X plus what? 2. Right. So now with this, we can deal with what? The numerator, then deal with what? The denominator. Because I've done what? My simplification. I'm done with my simplification. So I can say that the limit as x approaches 1 of 1 all on the limit as x approaches 1 of what? X plus 2. This one. Then I move again. We can say that you maintain that, then the limit as x approaches 1 of 1 all on, then this one we are adding, right? So I can take the limit throughout. So the limit as x approaches 1 of x plus the limit as x approaches 1 of 2. That's that. So this, so I can continue here, right? So which is the limit of a constant as x approaches 1 gives what? 1. All on the limit as x approaches 1 of this x, we plug in the value, so we get 1, right? Plus the limit as x approaches 1 of this 2 is what? 2, because the limit of a constant is the same thing as the constant. So I have 1 all on 1 plus 2, which is what? 3. So this is the limiting value. That is the limiting value. So as you can see, I believe you understand what I was saying plenty. So your more question now, I also to check say that question way meet my simplification and now, or I can do direct substitution. Some question allows you to do what? Direct substitution without any simplification. But some questions na sword thing or my direct substitution and just say you have to what? Simplify, reducing and some with me I direct substitution. Do you understand that? Alright. So now let's see. Next question. Let's see the next question. So we have, it said evaluate this limit. So this one is our next question too. Evaluate this limit as x approaches 5 of x squared minus 5 all on x minus 5. So we have this. The limit as x approaches 5 of this x squared minus 5 all on x minus 5. So how will you, x minus 25, yes, x minus 25. So how will you solve this question? This one is very, very simple. Let me think myself. Solution. So how will you do that? Now, here you cannot do what? Direct substitution. Because when you substitute 5 here, you get 5 squared, which is 25. 25 minus 25 is 0. 5 minus 5 is 0. So you get 0 and 0. Unless you have to do further checks. So simplify. So here, I have x squared minus 25. You know that that's what? The numerator is difference of 2 squares. Which is x squared minus what? 5 or what? Squared. I believe you know that. So I can say that the limit as x approaches 5 of x squared minus 5 all squared all on what? X minus 5, right? So I can go again and then say that the limit as x approaches 5 of this x squared minus 5 squared is the same thing as what? X plus 5 then x minus 5 from difference of 2 squares all on x minus 5 all on x minus 5. All on x minus 5. So I can say that this x minus 5 cancels that x minus 5, right? So leaving the limit as x approaches 5 of this x plus 5. See, it's very simple. Now we can proceed again and say that the limit as x approaches 5 of what? X plus the limit as x approaches 5 of 5. So very, 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 very simple. Very, very simple. Now the limit as x approaches 5 of this variable x, you plug in wherever you see x, you plug in 5. So I get to 5 plus, here the limit of a constant is what? The same constant, which is 5. So 5 plus 5 gives 10. So this is the limiting value. That's the limiting value. That's the limiting value. Alright, so that's the limiting value. So you can go to the check. Check. All right. So let's see last example. because this is very simple. So let's see last example. Then we move.